Hello, hope you're having a nice day. This video is going to cover the two fabled numbers on a dyno sheet, power and torque, and what they have to do with your car's acceleration. In the next chapter we'll go through the maths to calculate it, but if you're just here for a quick answer, here's the too long didn't watch. When you're looking at the end result, acceleration, power is all that really matters. Here's an extreme example. Imagine two identical cars. Every single detail about them is the same. Their weight, their aerodynamics, their torque curves, and so on. We'll set them up with continuously variable transmissions which can hold the car at any RPM we want while their speeds increases. For the sake of this example, these are perfect transmissions that can hold the car at a precise RPM and never stray from it. We'll set one car to never leave peak power and the other car to never leave peak torque, so any variable in this experiment are power and torque numbers. Obviously this isn't a real world situation, but it answers the question of power or torque. So which car's faster? The car at peak power. Now let's talk about how to do a rough calculation yourself. It might be worth following along on a spreadsheet. I'm a big fan of doing that to help understand equations. And for this explanation I'm going to be ignoring drag and rolling resistance. It's not needed to explain this, but know that we are simplifying things a little. Power is simply force multiplied by speed. In a car, the crankshaft is spinning, so the force is a turning force, torque. For the same reason, speed in this case is rotational velocity. Multiply them together, you get power. Your units with torque may vary. Most of the world uses either pounds-feet or newton meters. Rotational velocity on the other hand is universal. Everywhere uses revolutions per minute, or RPM. To get power you can either have a lot of torque and spin slowly, like a truck engine, or have no torque and spin really fast, like a sports bike. Both have their pros and cons. You don't want to be screaming to the rev limiter just to tow a trailer out of a car park, but on a racetrack you're always chasing the red line, so a small, high revving engine isn't bad, and usually lighter. Torque is one half of the power equation. More torque means more power, you don't get one without the other, but power is a unit we care about because it also shows how quickly the torque is being applied. One engine might have half the torque of another engine, but if it's running at twice the speed, then the end result is the same. And that's why smaller engines can make up the torque deficit by revving high. This doesn't mean that torque isn't important. It is useful for understanding what's going on in the engine, but the easiest way to decide which car is faster is by looking at power. Horsepower is calculated with pounds-feet multiplied by RPM divided by 5,252 to make the units work. If you're using newton meters for torque, you're dividing by 7,127. This is because imperial units are never fun and always awkward. As an aside, the number you're dividing by shapes the graph. If you're using pounds-feet, you'll have more power than torque above 5,252 RPM, no matter how much torque you have, and the opposite is also true. Below 5,252 RPM, you'll have less power than torque. So if you ever hear of anyone talking about how their car has more torque than power, all that means is that it doesn't rev very high. Now let's ditch imperialism and go to SI units. We'll take a power curve in pounds-feet and RPM and convert the torque to newton meters and RPM to radians per second. The easiest way to convert pounds-feet to newton meters is just to Google the conversion rate. Radians per second might be a unit you've never heard of, which is fine, it only ever really comes up in situations like this. All you need to know is that a radian is just another way of measuring angle. Radians per second is an alternative to RPM. It's also far cooler because it gets shortened to rads. To convert RPM to radians per second, multiply it by 2 pi, divide by 60. To get power at any point in the curve, multiply rads by newton meters. For power we'll be using watts instead of horsepower, so you can finally compare your car to your microwave. Australia, for all their weird upside down spider wrangling ways, understands this and uses kilowatts to measure power. Here's a power curve I made for demonstration. This engine makes 300 pounds-feet of torque at 5,000 RPM, producing 285 horsepower. Or in our freaky SI way, that car has 407 newton meters of torque at 523 radians per second, producing about 213,000 watts. You can probably see why Australia uses kilowatts, since that drops off 3 digits and makes it a way more manageable number. Now, after putting so much emphasis on SI units, I'm still going to be giving examples using imperial. Why? Because those are numbers you'll probably understand a lot better, so mean a lot more. I'd much rather do calculations in SI units, but I think more people understand the magnitude of 76 miles per hour than 34 meters per second, for example. To get the force accelerating the car, you need to take the power in watts and divide by the speed you're going, in meters per second. In a real car you can measure it, but since this is a hypothetical car, we'll actually calculate how fast we're going at any RPM. For that, we need the gear ratio, the final drive, and the wheel radius. In this case, we'll set both the gear ratio and final drive to be 3, and for the wheel radius, I'll use 0.3 meters. Take the speed of the engine in rads, multiply it by the wheel radius, and then divide by the gear ratio to the wheels. In a spreadsheet, we can easily do this for every RPM value we've got, like so. Then we've got the speed we're going, how much power we're making there, so we just divide power by speed and you get the force pushing the car. Finally, we're calling on Newton's second law and rearranging that to get acceleration, which means all you need to do is divide the force by how heavy the car is in kilograms. If our car has 285 horsepower at 39 miles per hour, that's a drive force of 12,200 newtons. If it weighs 1,000 kilograms, then that means it'll accelerate at 12.2 meters per second squared, or 1.24 g. And that's why we talk about cars in power to weight, not torque to weight. So to summarise, get the engine stats, convert to SI units, find the speed you're going at each RPM, divide power by speed to get force, divide force by weight to get acceleration. Some observations now. A graph of drive force, torque and acceleration make the same shaped curve. They're clearly correlated. When you're in a gear, you have the most drive force when you have the most torque. This is why in first gear, launching at peak torque will get you from a standstill the fastest. Once you're moving, you never want to stray far from peak power. Let's show this by making an adjustment to the example. The car we just created has a peak acceleration of 1.24 g, and that was at peak torque. Let's say the driver decides to downshift, so again the same speed, but now at 7,500 RPM, where the car's making 50 pounds-feet less torque, but 70 horsepower more. Well, now they're accelerating at 1.56 g. Peak torque might be where the highest drive force is, but if you use gearing to be in an RPM with more power, you'll accelerate faster. I think another way of describing this is that power is where the benefit of torque and the benefit of short gearing come together to give you the best acceleration. Power being so crucial is why electric cars can get away with having one gear, or occasionally a 2-speed. Electric motors broadly have a power curve like this. They start with a lot of torque, dropping off quickly, while power rises before reaching a plateau all the way to the RPM limit. Since power doesn't change a lot, there's no advantage to having more gears. You can't drop a gear to reach a better point in the power band because there's no point. The electric cars that do have 2 gears use one to get into the power band as quickly as possible, and after that I'll upshift and stay there until you stop. Let's finally talk about gearing. Your gearing simply controls what RPM the engine is running at when doing a certain speed. As a result, you want your gears to be close as possible while still covering a usable speed range. A great ballpark method to set your gears is to figure out what range of speed you're covering, and then divide by the number of gears you've got. So if you know that you're doing a time attack lap and the slowest corner is 40 miles per hour, the fastest straight is 160, you've got a range of 120 miles per hour. If you have 6 gears, that would mean you could just set each one to cover 20 miles per hour. So set the first one to top out at 60, the second one to top out at 80, and so on. Just want to get that out there somehow, because I found it useful. And I think that just about covers everything. Anyway, thank you for watching. Remember to subscribe to Boost and Ethanol for more, leave a like if you've enjoyed, and ask any questions you might have in the comments. Goodbye.